Okay. So substrate, it is like this. I'll be taking a box from here and assigning the values like this. Then substrate, double click, material, you will see the edit. From edit, you can go to the library and select type whatever material you want. Okay, like that. So next is the next I will draw the ground plane. So ground plane, it will be coming at the back of the substrate. We can give the name as ground plane itself. It is again the same size of the substrate. Then I'm going to align this. It should be below the substrate, right? So that is why I'm giving minus substrate H here. So it will be aligned behind the substrate like this. Is this clear? Is the step is clear?
Yes, ma'am.
Okay. So, and the ground plane is a conducting plane. So we have to align conductivity or conducting planes so that we have click on ground plane, right click on that, assign boundary and perfect T. Okay. So it is coming as a conduction plane. It will be a metal. It can be copper or aluminum, whatever we want. So it will be basically a metal sheet. And next is the patch. Patch is an ellipse. So for the ellipse, actually we need major radius and the ratio. That is major radius to minor radius. So those values I will take from here. Okay, this is the equation. Patch x by 2, patch x by patch y. That is patch length by 2. I have given patch length instead of x. That is patch x by patch y. So based on the structure of, that is an equation that I have created. So that optimization will be easy. Patch length by patch width. One second, why it is. It has come more than this, right? This is y2. Okay. Okay. This is the equation that I got it from one paper. People used to design the ellipse. So again, we have to assign a boundary that is perfect E2 because it's a conducting one. So next is the port. For the port, actually there are so many connectors called SMA connector, Tnc connector, Bnc connector and all. It is like which frequency we want. Based on that, we will select the connector. For also like the weight of the antenna. If our antenna is a heavy weight, we cannot go for SMA because SMA is a very small connector. If you want, I can show the pictures also for the SMA. SMA connector. This is an SMA connector. So you can see here, this is a male version and this is a female version. So in this, you can see we will be using the female version, like with this flange. So the inner conductor, the inner conductor that we will be soldering to the patch, and the outer conductors, that is this 4 legs, we will be connecting to the ground. Like this, we will be soldering the connector to the antenna. Huh?
I'm not able to see screen, ma'am.
You are not able to see the screen? Ma'am, you can see my screen?
No, screen is fixed. It is not moving.
Like you people cannot see the SMA connector one.
Yes,
Yes,
yes.
ma'am.
Okay, okay. I'll stop sharing and again I will share my screen. Now, is this
Yes,
visible?
Yes, ma'am.
Yes.
Ma'am? Okay.
Yes,
So
sir.
this is called SMA connector. Here you can see this is a female connector and this is a male connector. Okay, so for every connector there is a female connector and a male connector, and for our antenna we will be using the male connector because here you can see a center conductor and other 4 legs. So center conductor will be soldered to the patch, and these 4 legs will be soldered to the ground plane.
Okay.
So our cable or the coaxial cable from where we are giving the power supply will be connected to this SMA connector, and this SMA connector will be 50 ohm impedance, standard impedance of 50 ohm, and with this SMA connector the antenna will get excited.
Okay.
So there are another connectors also. I can show you Tnc connector. So this is a Tnc connector. You can see my screen, right?
Yes, ma'am.
Okay, Tnc connector, it is little more big. So if we are designing some antennas like big structures, like horn antenna and all, that
Okay.
time we cannot use SMA because it is a very small connector. It can the antenna cannot withstand, or the connector cannot withstand the antenna's weight. That is why we'll go for the Tnc connector.
Okay.
But all the connectors are having 50 ohm impedance. All the connectors will be having the same impedance. That is not an issue based on some mechanical parameters, and also there is a frequency range for the connectors. So based on that, we will be using the connectors. But for the patch antenna, usually we'll be using the SMA connector. So I'm gonna design
Okay.
an SMA connector for our structure. This is like the practically what we are using is a coaxial connector, and I'm gonna design the coaxial connector with the antenna instead of instead of drawing any other rectangle and lump port. So this is our design. You are able to see this HFSS screen?
No, ma'am.
No? Yeah,
Yes.
I'll show.
No.
No, okay, I'll again share my screen. So now,
Yes, ma'am.
yeah,
Yes.
okay. So first is a cylinder or the inner conductor I'm going to design. I took a cylinder and I made a structure. So the property will tell that this is inner conductor, inner coax, I'll name it as. And this is again, it is a perfect electric conductor. PEC is perfect electric conductor. I took PEC and I'll assign the coordinate. Inner coax.
By the sound.
Radius is inner coax I gave. It is 0.5 actually. And the height is like, height is not a matter for the coaxial cable. Height is not affecting the impedance. So here our height is the substrate height I am giving. So you can see it is aligned here, right?
Yes, ma'am.
And another, it is a making a Teflon coating, because in every connector you have seen now one white is covering it. Did you observe that?
Reading.
Like, okay, I'll show that. Here you can see now one inner conductor. Now you can see, right, my screen?
Yes, ma'am.
Yeah, here you can see one inner conductor and there's a Teflon coating.
Okay.
So actually this is this Teflon coating, it is affecting or it is making the 50 ohm impedance for the connector.
Okay, ma'am.
Okay, so that
Okay.
I'm going to design. The value of that is 0.75 mm, that is the radius, and height is again I'm giving substrate H. So you can see this. Right?
Yes, ma'am.
So for this connector design, there is a thing that is we have to actually, then again we have to draw a circle here. So where we have to give the port, because we have to draw a port, right? Circle of radius in Teflon radius. So it is covering the entire one. So what I have to do is, this is the procedure that we should follow for the coaxial cable design. First, from the ground plane, we have to subtract this. And for subtraction, we have to clone this shape, because when we are cloning, I will show you the without cloning also. Cloning, the circle will remain, like that arrow will remain, so that we can later on, if we want to modify, we don't have to go inside and do the things. So here you can see it is
Okay.
subtracted, but this is remain as circle itself. So I am assigning a perfect T for this also. So circle it is remaining, but it is subtracted already from the ground plane. But so if you are not doing the cloning, subtract ground plane and circle. If you are not doing the cloning, there is like if you want to see the circle, you have to go here. So like if you have many components, that will be like you cannot take, or it is time consuming. That is why I'm going for cloning. It won't make any difference. Only thing is it makes our design more easy. Clone, yeah. And the circle is remaining here. So another thing is that this is passing through this taconic ceramic and the other thing, the cylinder. This is the cylinder, no? So this cylinder, that is a Teflon. I didn't assign the material, so I have to assign a material. So I forgot that. I put Teflon. Teflon, you can see it is having relative permittivity of 2.1. I assigned Teflon also for this. Then these two things that from the substrate we have to subtract because it is penetrated through this cylinder 1 and inner coax. Clone, okay. So now we can draw a with the circle we can draw the port. So before that, I just want to check here. Is up to this it is clear, right? Hello.
Yes, ma'am.
This is actually like you have to practice how to do this because it is little, what to say, it is like a format that you have to follow. Okay, this is excitation. I'm taking the circle, right click on that, assign excitation, lump port. Next, new line. Cancel, I'm sorry. So like from the outer to the inner, I have drawn a port. So that will be connected to the upper side of the patch.
Okay.
Like this current will be flowing. So again, the next step is we have to give the frequency. So like what all things we have to give here, you can see it is missing analysis setup. So go to analysis setup because we didn't give any frequency value. Analysis, add solution setup, we'll give 2.4. And click on this plus setup, right click, add frequency sweep 1 to 5, just give 1 to 5. and I'm giving fast. There are three: discrete, fast, and interpolating. So fast, it will be very fast simulation, and interpolating, in the interpolating also it is very fast, but we won't get the field data, like gain value we won't get. Discrete, it will take, it is doing accurate calculation, but it is not fast. It will take each and every point of frequency. The result will be very accurate, but it will take more time. So at the end of the design, after we are getting the result, to conclude that or to make sure that we will go to discrete. Otherwise, we'll only go for fast. And another one more thing, we have to give a boundary box here. Why we are giving boundary box? Because we are creating a far field, and according to the antenna theory, we are measuring the, we have to measure the antenna parameters in the far field. Then only we will get a perfect TEM. So this step, I think last class we have discussed, no? Hello?
Yes, ma'am.
Okay.
Ma'am,
Ma'am,
once
you
again
are
you can
also getting, no?
Yes, Sadhana. Yes.
Okay. Absolute, I'm giving 30. Actually, theoretically, what we used to do is, it is very big. I'll delete this.
Ma'am,
Huh.
previous step once again can you tell?
This step.
Yes, ma'am.
Okay. This step, actually, we have to give a far field boundary. Why we are taking a far field is that antenna measurements are all taken in the far field. Because actually the electromagnetic waves are propagating perpendicularly, that is E and H will be perpendicular, and there are so many modes for the propagation of the electromagnetic waves. So for the accurate results or the accurate calculation, we need transverse electric mode. That means the electric field will be should be exactly perpendicular to the magnetic field. Then only we will get the correct result. That will happen after some distance, like after a distance of lambda by 2 or 2d square by lambda, we will say.
Okay.
D is the greatest dimension or the largest dimension of the antenna. So at a distance greater than 2d square by lambda, the antenna far field will begin, and after that at any field you can measure the antenna parameters. But for the simulation, what we will do is we will take a boundary from the edge of the antenna greater than lambda by 2 distance. So from from lambda by 2 you can measure the structure.
Okay.
I'm giving 20. It will be like or greater than lambda. 20 will be greater than lambda. You can see now it is like quite a far distance from each of the sides.
Yes.
You can go for percentage offset also, but percentage offset you have to give like if you want to give separate values. Like if you are going for percentage offset 10. Okay, this is like only on one direction it is giving. See x only in x, y and z, plus only in the plus direction. So in minus direction it is not coming. So instead of that, if we are giving absolute, it is more faster. Like it is more convenient. It will align like this. And for the region, it is a radiation box. So we have to give radiation box like we are giving perfect T and all for the conductors. So right click on the region, assign boundary, radiation. So radiating only. This will act as a radiation box. Here in the boundaries, you can see all this. Perfect E1, perfect E2, perfect E3. That is the circle that we have drawn for the port. and the radiation box. Hello?
Yes, ma'am.
Actually, ma'am got lost, I guess. Hello? Ma'am? Hello? Ma'am?
Adra,
Hello?
my internet connection is very weak. My connection is very weak. So you go
Oh,
ahead. I learn from recordings.
okay, okay, ma'am. Okay, okay.
Okay.
Okay. So after seeing the recording, if you're getting any doubt, you can call me, ma'am. Okay. So like this, okay, fine. Then it is done, right? We have to save it. You can check here and on the tick bar that everything, the 3D model is fine. Next is the simulation. Simulation, this one, it is going on. So our aim is to design an antenna which is resonating at 2.4. So we'll check the result. So for the result, first we have to check S parameter, and S parameter should come below minus 10 dB. Correct?
Yes, ma'am.
So result, right click, create model solution data report, rectangular plot, S parameter S11 dB, new report. So here anything is resonating. Gautam?
No, ma'am. Seeing
No,
it.
right? Nothing is resonating.
Yes, ma'am.
Yeah. So, like it is, I'm going step by step actually. That is why. So, we don't have to take the other results because the antenna is not at all resonating. So, we'll go to the structure
Yes.
again. So, what I have done actually, I change the feed
Mm.
position. So, based on the feed position, we can tune the structure so that it is resonating at 2.4. So here in this, you can see the feed position is not in the near to the or not aligned to the origin. It is moved little bit.
Yes, ma'am. Yes, ma'am.
Yeah. So that will also take that will also cause the frequency to resonate. So here I will just see where it is moved. Or I can see here itself feed offset will be there. Okay, there is a term called feed X and feed Y. So I'll add the same here in our design. Feed X and feed Y. So what is the value of that? Okay. These are the values I got through optimization. So don't worry about the values. I'll teach you how to do
Yes.
optimization, but not in the stage. You won't understand by the stage. That is why I'm not going for that.
Okay, ma'am.
So this Teflon, it is moved. So like that, we have to move the inner coax and the circle. You don't have a doubt, right? You are getting right
No, ma'am. Yes,
completely?
ma'am.
Okay.
Yes, ma'am.
So you can see now it is moved a little bit.
Yes, ma'am.
So I'm saving, checking, 3D model is fine. Going for the simulation. Okay, simulation is completed. So we can go for the S11 plot. Okay, here now see, something has come, right?
Yes, ma'am.
So that is because I changed the feed position. So everything in the design, it is matters. So here,
Okay.
I just want to see like which point it is resonating. So I took this marker, add marker, and I'm putting on this point. I can see in 2.4 it is just started resonating at, so because it is showing minus 10.7, right?
Yes, ma'am.
So other than 2.4, no other frequencies it is resonating, but at 2.4 we can get the frequency at minus 10. Like the S parameter value is minus 10.7, that means at 2.4 the antenna is resonating.
Yes, ma'am.
So when we go for practical, no, like when we design it, usually we will design greater than minus 12 dB or something. So that when we'll go for fabrication, we'll get the results. Otherwise, this 10 can go up, no, like because of the fabrication errors and all during the manufacturing process. So for a margin, for the fabrication, we'll be designing greater than minus 12 dB. And next
Okay.
parameter is the VSWR flow. So create model solution data report, rectangle plot. Here in this window, you can see there are so many parameters, Y plot, Z parameter is the impedance parameter. So VSWR, so we have to take the VSWR and analyze. VSWR, it is a unitless quantity, so it is an absolute value.
Okay.
You are getting my voice? You are getting my screen?
Yes, ma'am.
Okay, okay.
Yes, ma'am.
VSWR doesn't have any unit, so we have to take an absolute value.
Okay.
Okay, a report.
Okay.
And ideally, the value of VSWR is 1, and ideal cases are not practical. So it is like 1 means full power is transferred. And we can get, if we are getting near to 1, so we can see 1 point, that is 2.4 is a resonating frequency. We are getting nearly 1.82, right?
Yes, ma'am.
So that is
Yes.
pretty good because we have to get below 2. And
Okay.
as we tune the S parameter, that is like if it is increasing and increasing, we will get very near to 1. VSWR very near to 1. So this S
Okay.
parameter and VSWR is related. You know the equation VSWR, like S parameter is equal to 1 plus VSWR divided by 1 minus VSWR.
Yes, ma'am.
Okay. So next parameter, we have to see the radiation box. Actually, in this design, now I didn't assign the radiation box. I'll assign the radiation box now. To see the gain, we have to assign the radiation box. So in this, you can see there's the radiation. And insert far field setup, infinite sphere. These values you have to give. That is phi 180 to 180 and theta 0 to 360. Step size of 10. Radiation sphere is also there. Another, if you want to see create model solution rectangular, Z parameter of dB10. No. This is coming up to 35 only. So it is dB10. Okay, leave it. So we have to simulate it again for the infinite sphere because we have added, it is completed. Next
Yes,
is again result, create far field report. Instead of going model solution data report, we have to go to far field report for the radiation pattern. So 3D
okay.
polar plot, gain, dB. Here you can see phi theta, family is also like at 2.4 we are taking. You can take here sweep. Sweep means entire sweep, it will come. Like from all the values, all the frequencies it will come. But our antenna is resonating only at 2.4. That is why I am taking last adaptive.
Okay.
So gain total dB because gain is measured in dB. New report. You can see the gain pattern, right? The gain
Yes,
it is
ma'am.
coming at the greatest value it is coming, or the value which is at the top, that is
Yes, ma'am.
1.28 dB gain is coming.
Yes, ma'am.
Okay, this
Yes,
is
ma'am.
the gain of the antenna currently.
Okay.
And usually people will see E plane and H plane pattern to see the beam width. So for that result, create far field radiation pattern. This is a 2D radiation pattern. This actually it is a 3D radiation pattern, and the pattern that we are going to see is the 2D radiation pattern. Gain
Okay.
dB, and we have to go for the azimuth pattern. There is a pattern called azimuth. I have teach you now the azimuth pattern and the elevation pattern. There are two patterns. Azimuth pattern means a horizontal pattern, and elevation pattern means a vertical pattern. So in
Okay.
antenna, everything we will speak in terms of r, theta, and phi. So to see the azimuth pattern, we have to make phi as 0. New report. You are getting the pattern, correct?
Yes, ma'am.
So in this, if you want to see okay, so in this you can see this is the pattern, and from the pattern usually what we'll measure the beam width. This is the main lobe, and here you can see 1.28. That is the maximum point which is coming at the 0 angle. 1.2879 dB is the gain that we got from the 3D pattern also, no?
Yes, ma'am.
Yeah, that we are getting here. So next is like we have to find the beam width, like how much it is the pattern is covering, like how much area the pattern is covering or antenna coverage. So actually you can do this trace characteristics add radiation. Sorry. This is for the side lobe actually. No. Okay, I will teach you. This is like, this is getting 1.2879 dB, right?
Yes, ma'am.
We have to actually according to the theory and even practically, the half power beam width is the point where we are getting minus 3 dB down. So if you do 1.2879 minus 3, you will be getting minus 1.7121. Locate that point in this radiation pattern. So 1.45 again. If I'll go 1.5, just I will be taking 1.5 instead of 1.7. So we are getting 100, no? The angle is 100.
Yes, ma'am.
So yeah, actually it should be 1.7. So I am considering 1.5. You understood, no?
Okay.
From the minus
Yes.
3 dB points. So minus 3 I am doing from 1.2879 or the maximum value of the beam. And I should get minus 1.7. If I am taking minus 1.5, that is 100. So because this is a symmetric pattern, you can see, no, both the sides are the same. It is aligned with a 0. So you can take the beam width as the 200 degree.
Okay.
Okay.
Okay, ma'am.
So and here if you see minus 0.12, that is the minor lobe radiation peak point. So the half power beam width is greater than 200 and minor lobe minus 0.1235 dB. And then the elevation pattern. Next is this is called E-plane pattern, and next is this is called H-plane pattern, and next is the E-plane pattern. That is the elevation pattern. Far field radiation pattern, gain dB, and here you have to take phi all and theta 90. New report. Sorry. 50 theta 90. Or otherwise if I'll go theta all and phi 90, that is also giving the same. New report. Yes, this is the what to say, the elevation pattern.
Okay.
Actually the antenna, it is horizontal, right?
Yes,
It is
ma'am.
placed horizontally. So we are only concerned about the H-plane pattern or the azimuth pattern because the radiation beam is pointing towards the horizontal side of the antenna, right?
Yes, ma'am.
Yeah. Here also if you want to see, it is 1.2879. This is also a symmetrical pattern.
Yes, ma'am.
So these are the components of the This I'll hide because of this we cannot see the structure. I just hide it. And if in this eye, if you want to see, you can just give tick mark. And if you want to hide something, just click on this and put that red mark. It is hiding.
Okay.
So like this it is. And other thing, if you want to like side chamfering you are seeing, right? Select edges. If I am selecting this edge, I'm not getting the 1 minute. Side I'm selecting, and here filleting and chamfering. Filleting, if I'm giving a filleting radius as 2, just you see how it is coming. It is coming like this, right?
Sure.
This is just a tuning technique. Or if you want to, like you have seen the buttons. And this is called chamfer. Chamfer, if I am making 2, this is cutting like this.
Okay.
Based on your shape, you can do like that. I just did chamfering there just to make like a button shape. That's all. So another thing is that if we want to do the next one, like what to say, a slot or something. So if you want to see how the current is flowing through this, perfect ellipse. I'm selecting this ellipse, plot field, E field, magnitude E. I will be seeing the current flowing through this. You can see, right? The current or the E field 1.84. This much current it is flowing. And where we are getting the red values. So where we are getting the red values, there the current will be flowing more. And you can see this this scale diagram. So where you are getting red color, then it is orange, then yellow, like that it is the value is decreasing. So at the center you are getting very least current, but it is after going it little farther away, it is getting higher and higher. So at the edges you can see, you can mark the red now. At this red part it is flowing more.
Hmm?
This red you can see, right?
Yes, ma'am.
This is where the current is flowing more.
Okay.
And if you want to see plot fields, E field, vector E, so we have to select a geometry actually. Plot fields, I will E field, vector E, all objects done. You can see it is flowing. So how it is flowing? So we can go for animate. Here itself animation will be there. Animate. Animation. Okay. So I have select vector. Vector only will be having direction. And you can see now the current is flowing. How the current is flowing.
Yes, ma'am.
This is the way current is flowing. And the current is flowing like current vectors are going vertically and vertically. And there is another thing also here, the axial ratio. Actually, if there are polarizations, right? I said now, there are polarizations. I am stopping this.
Yes, ma'am.
So for a circular polarization, the axial ratio should be less than 3 dB. So I designed this antenna for circular polarization. So I want to check whether I am getting a circular polarization. That is why I draw a circle. There are advantages of circular polarization, like you can actually accept the horizontal and vertical polarizations with 90-degree of phase shift. In this case, vertical polarization can only take vertically polarized waves. Horizontal polarized antenna can take only horizontally polarized waves, but circular polarization can take more both the horizontal and vertical.
Okay.
That is why, like for the critical application, kind of we'll be designing an antenna with a circular polarization. Like you can see the satellite antennas and all, it will be in circular polarization.
Okay.
And if I design my antenna for circular polarization, I want to check whether it is circularly polarizing. Create model solution report, rectangle plot. I am gonna check my axial ratio. So yeah, axial ratio. Axial ratio in dB. I'm gonna check. Okay. This is coming in all the frequencies, all the phases. Okay. It rectangular plot, far field, rectangular plot, axial ratio in dB, theta all, I0, 2.4 gigahertz. So I'm getting a very high value, 70. So my antenna is not at all circularly polarized. Check in 90 also.
Okay.
So here also you can see it is not circularly polarized, right?
Sorry. Yes, ma'am.
So I have to modify my structure so that I should get, it is only the acceleration is mainly because depending on the structure. So how I am drawing the structures, I should include more circles to be circularly polarized. So if I am doing a chamfering, what will happen? We'll see. Chamfering, like filleting, not chamfering, filleting. I'm giving a 4. All the edges I am giving some 4. I'm simulating because this is also a curvy structure, no? That will account for the axial ratio. That is why. So you can see after chamfering, the 2.4 value, it is again increased to -16.
Yes, ma'am.
VSWR 1.33, a good value.
Yes,
And gain 1.4 instead of 1.2. Again the radiation pattern. That is like the same, but only thing is that it is improved. And the axial ratio. This has come down. Take dB value. This has not come down. This is actually little come down, but not much. So like this, I will be including more structures, and tomorrow I will show you like how to cut the plot and all those things.
Okay, ma'am.
Okay. Okay, tomorrow also we'll have a class.
Okay, ma'am.
Okay. Ma'am,
Okay, Andra.
okay, I will send this to both of you.
Okay.
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 Okay, okay. Okay then bye. Bye ma'am. Bye Gautam.
Bye. Bye.
Bye.
Bye.
Yeah.